Good afternoon, everyone. Today we are hosting Ondřej Pejcha from Institute of Theoretical Physics at Charles University in Prague. And Ondřej was studying in Prague, then he moved for a PhD to Ohio State University. Then you spent some time in Princeton, and he's back in Prague. And he received the ERC grant for working on some aspects of binarity of stars. And the title of his talk is Exploring Common Envelope Evolution Across 1D, 2D, and 3D. Ondřej, the floor is yours.
Okay, thank you very much. It's great to be here again after 8.5 years ago. So I checked this morning that I was here in October 2016. So I will be able to give you an update of what I've been up to over this time. So Milena said the title of my talk, but my subtitle is a little bit mysterious, from Cat in Hat to Rogalov, and that alludes to the happy fact that I'm starting a second ERC grant in a month or so, and those are the acronyms which always have to be fancy for or funny, at least for the ERC. So I will also talk a little bit more about the plans that I have for the next 5 or 6 years in this regard. And the results that I will be showing today are mostly results that were led by postdocs and students in my group, financed by the first ERC grants. So I worked with 2 postdocs, Diego Calderon, who is now a Humboldt Fellow at Garching, and Damien Gagnier, who is now at Heidelberg. And 4 PhD students, Camille is now a postdoc at Leuven. Milan moved about a month ago to Ohio State, which is a complete coincidence. Worked on, or he could have as well moved to Australia. And Jakub, who is graduating this summer and has a position at Tartu Observatory lined up. So I will begin by quickly repeating the importance of stars, massive stars, and binary stars. But I believe that most of the people here are familiar with the basic motivations. So I will try to be very quick. Stars, and especially massive stars, are important site for synthesis of new chemical elements. And their evolution ends with formation of compact objects such as white dwarfs, neutron stars, and black holes, which are important for large areas of astrophysics. The deaths of these stars, especially of massive stars, put out a lot of energy and momentum into their surroundings, and as a result, these stars can affect evolution of entire galaxies. And finally, stars, and again especially massive stars, are very important sites of multi-messenger emission, including neutrinos, which we detected from supernova 1987A, and more recently gravitational waves. Most of my talk will be about binary stars, so I will quickly flesh out some of the most basic concepts. So here I'm showing the Roche potential, which is a very useful way of describing how physical processes happen in a binary star. So in Roche potential, we go to a coordinate system that's corrotating with 2-point masses on a circular orbit. And this Roche potential is composed of contributions from gravitational attraction and centrifugal acceleration. And as a result, the Roche potential has several saddle points, Lagrange points, which are very important for the dynamics, because these are the regions through which mass can flow between the 2 stars or away from the binary. And as a result of this Roche potential, we have several basic configurations of binaries. Either the two stars are detached, or one overflows its Roche lobe, sending mass to the companion, or the two stars both overflow their Roche lobes, and we have a contact binary. The final configuration here corresponds to a special case of sort of an infinite mass ratio where we have a single star that is critically rotating. Another basic thing in the beginning is the realization, both from observations and theory, that binary interactions are very frequent and that they strongly affect populations of stars and especially of massive stars. So the diagram on the left shows the companion frequency of stars as a function of their mass. And you can see that for massive stars, that means more massive than about 8 times the mass of our sun, the companion frequency increases beyond 1, which means that most of these stars actually live in triples or higher order multiples. And the pie chart on the right is a result of combination of observations with theory. And it tells us that only about a third of massive stars actually evolve as effectively single without ever interacting with their binary companion. For the remaining stars, about a quarter merges with their companion into an object that is potentially exotic. A third experiences envelope stripping, and some smaller fractions, significant accretion, spin-up, or potentially common envelope evolution. And these strong binary interactions are also quite frequent. Observations, but also theory, suggest that we have a merger of two stars in our galaxy approximately every 5 years, which is way more favorable and comparable to something like a PhD student timescale than a supernova explosion, where supernova explosion should happen every optimistically 30 years, but maybe every 100 years or less frequently. So what are some of the examples of interactions of stars in binaries? And I will show two specific cases and one general evolutionary pathway, which illustrates the diversity of what can happen in binaries. So the first case that I would like to mention is Eta Carina, which is a very massive star, about 100 solar masses, and that is surrounded by a homunculus nebula. This nebula was created during the great eruption of Eta Carina in the middle of 19th century, when the star decided to eject about 15 solar masses of its material. And you can see that the shape of this nebula is approximately bipolar, which is sort of a hint that binarity probably had something to do with it. In this case, it is natural to assume that the binary orbital plane was oriented along this region here, and material expanded in these bipolar lobes perpendicular to the orbital plane. Second example that is of quite interest is the progenitor of supernova 1987A. Supernova is very famous because we recorded neutrinos from it, but its progenitor was peculiar in a number of aspects, and an element here to consider is that the progenitor was surrounded by 3 rings, which are shown on this picture. There was an equatorial ring and 2 outer rings. These 3 rings are concentric. They share the same axis, but their centers are offset. And there are a number of possible explanations for this, but perhaps the most exciting one or the best one is that the progenitor of the supernova merged with its companion approximately 20,000 years before it exploded as a supernova. And final example that I would like to make is a picture from a paper by Chris Belczynski, which shows an evolutionary pathway that can lead to gravitational wave mergers. And what is shown in this diagram is evolution. Here is a time axis in millions of years. Here is separation of the two stars in solar radii. Eccentricity, not very important, but we have the masses of the two stars here and here, and also their evolutionary stages indicated. And what you can see is that this evolutionary pathway has sort of two critical phenomena that determine the outcome, and that also allow this pathway to form two black holes that eventually merge by gravitational wave emission. The two important components that also bring a lot of uncertainties are collapse of a star to a black hole, which occurs twice for both stars. And the phenomenon of collapse of massive stars was the subject of my PhD and early years of my postdoc. And it is possible that I talked about it while I was here in 2016. I don't remember what I talked about, but you know, that was my main topic back then. The other important phase, which has been on my mind for basically since that time, is the common envelope evolution here, which is very schematically indicated by this ellipse. And you can see that in this phase, basically in zero time, there is no time difference here. The black hole accreted a little bit of mass. The companion lost almost 50 solar masses of material, and the binary separation shrank by almost a factor of 100. So common envelope evolution is sort of the crucial part of this trajectory, which brings the two objects so close together that ultimately 10 billion years later, they can merge by emission of gravitational waves. But common envelope evolution has a much wider range of applications. It was actually invented in 1970s by Paczynski and Oestreicher in the context of low mass and high mass stars. And in common envelope evolution, we take a binary where one star is likely evolved on a wide orbit, and something happens, common envelope, and we either get a closed binary or the two stars merge into a single object. And this element in the evolutionary pathway leads to a number of interesting objects that are studied by large parts of astrophysics, such as X-ray binaries, cataclysmic variables, all sorts of double compact object binaries, or peculiar objects such as the ones that I listed here. So the question is, how does common envelope evolution work? And the importance of this phase is accompanied by the fact that this is also one of the least understood major evolutionary phases of binary star evolution. So it's a place where there is significant uncertainty into how things work and what eventually happens. And this very much affects all sorts of predictions and explanations for many areas of astrophysics, including gravitational wave sources. So in sort of a very simple picture, the common envelope evolution happens when we have some star that is evolved. Think of red giant or red supergiant, which has a core. And then we have a companion that enters this star and spirals to the center because it experiences drag. And from this picture, we see immediately the first difficulty with studying this phase theoretically. The reason for this is that we would ideally like to resolve simultaneously the entire star, which would easily be several astronomical units large. And simultaneously, we probably should resolve physical processes close to the core or the companion that enters. And if the companion is a neutron star or a black hole, we would need to resolve processes on scale that is less than kilometers. So why is that? The reason for this is that accretion, for example, on a black hole could create significant feedback that is easily able to eject envelope of the star. So for a long time and up to this date, people have tried to come up with relatively simple prescriptions for what happens in common envelope evolution. So if we assume that everything happens very fast and there is no significant loss of energy to the surroundings or gain of energy from, say, nuclear reactions, we can write a simple energy conservation. Here, the orbital energy before and after interaction is subtracted and is made equal to the binding energy of the envelope with some constant of proportionality, which hides everything that we do not know. And I, in some sense, love this equation because simultaneously, it's something that I can explain to almost anybody within 2 minutes. And at the same time, it's effectively the state of the art that is used in binary population synthesis. Nonetheless, we should strive to understand common envelope evolution better. So here I will show different phases or stages of common envelope evolution, which are best visualized using a time axis, which has an origin at a point when the dynamical interaction is strongest. And I will explain later what that means. The time then proceeds before and after this point of strongest dynamical interaction. And you can notice that the time axis is logarithmic, so it goes a long time before and a long time after. And the time is measured approximately in dynamical timescales of the object. That means before the interaction in orbital periods, and after the interaction, it's either orbital periods or dynamical timescale of the star that survived. And traditionally, people recognize these stages of common envelope evolution, where we start with a normal binary star, which, due to various reasons, can experience loss of corrotation. That means the companion enters a non-corrotating envelope, and that leads to a dynamical plunging. So the two cores approach each other very fast. And after that, what can happen is a self-regulated spiraling where the two cores orbit inside a shared envelope until the post-common envelope binary or a single object emerges. So that's the general picture, but what kind of theoretical tools do we have to describe this phase? Traditionally, people have used two tools. One is 1D stellar evolution, which is very good for studying the system when either of the star is very spherical. On the opposite end, we have multidimensional explicit hydrodynamics, which is very good for studying the strongest dynamical interactions that exist in the system. However, this multidimensional hydro cannot be run for a long time because we simply can take only a limited number of time steps in a computer. And the result of this is that we do not really have good tools that would be connecting the individual phases of this evolution. And that is potentially a big problem because these phases do not occur in isolation. One follows from the previous one. So if the theoretical tools are not great, what kind of observations can we use? And again, for a long time, we sort of could only study binary star populations before entering this, this phase, or after this phase has long concluded. But in more recent years, there has been a new important development in a large part to thanks to people working here in Poland, and also especially thanks to data from OGLE, which were very important in all of this. And as a result, we now know a class of brightening transients that are associated with this common envelope evolution, which we can study. And also we can study remnants of these interactions over potentially long time scales, like years, decades, or maybe centuries. So what I will focus on in the rest of my talk is this part of the parameter space, focusing on these three phases of common envelope evolution. And I will illustrate them with some selected results from my group. So the first part of my talk will, or of the rest of my talk, will refer to the question, which stars enter common envelope evolution? And here I will show three results that we achieved. In the second part, I will talk a little bit about the transients that are associated with common envelope evolution. And finally, I will show some movies of hydro simulations that describe how the binary emerges out of common envelope. So let's begin. The first possibility how a binary can enter common envelope evolution is through mass transfer and its instability. So this is probably familiar. Star expands over its rho slope, starts transferring mass to the companion. And if this mass transfer gets very strong, material can leave the binary from around the L2 point. And both of these processes will make the binary unstable, reduce the separation, and that leads to the dynamical plunging. So when we are studying binary evolution in codes like MESA, we need to be able to calculate the rate of mass transfer from one star to the other, m dot. And traditionally, these calculations have been done on sort of a framework that was built by Kolb and Ritter at late 80s and early 90s. And that effectively relies on the assumption that material moves on equipotentials until it reaches L1 and then goes to a companion. So with my student Jakub Cehula, we decided to look at this problem differently. We constructed a new model where we obtain 1D equations by averaging 3D Euler equations. And in this model, the mass transfer rate is calculated as an eigenvalue of a two-point boundary value problem. So similar calculation to what is done for stellar winds. And the result of our work is that there is systematic uncertainty in calculating this m dot by a factor of 2 to 4, which obviously affects which stars become unstable and which stars remain stable. So the way to think about our result here is that we do not claim to provide a superior model. We claim to construct a different model built on different assumptions and trying to see what are the differences in the answers. The reason for this is that mass transfer through this L1 point is inherently three-dimensional phenomenon, and we are trying to find out some kind of one-dimensional approximation to it that we can solve. And a second result comes from a paper that was actually submitted earlier this morning to monthly notices. And that's a result of work where we included radiation into this model in a way that is not taken into account by stellar evolution codes like MESA. And what we found out is that for some stars, there is a possibility that radiation gives this mass transfer an extra boost, and that could be some element that that helps with explaining outbursts of luminous blue variables. At this point, I would like to remind or explicitly show that as binary is transferring mass and this mass transfer rate increases, the companion cannot accept all of it. And as a result, the binary starts shedding material to its surroundings. So this movie here is a result of simulations that I did still back when I was at Princeton. This is actually sort of geared at interpreting V1309 Scorpii. But for this talk, I would like to emphasize that as the mass transfer proceeds and m dot increases, the binary loses substantial amount of material in its orbital plane. The second way that a binary can become unstable is a situation where the companion is on an eccentric orbit, and as the primary star expands, the companion starts grazing this envelope. So here, what we did for this possibility with my PhD student, Kamil Landry, was that we constructed 3D simulations with SPH that took into account, in a relatively simple way, radiative cooling, radiative pressure, and dust formation. And the idea was that if we take these effects into account, the mass ejection that accompanies this grazing interaction becomes asymmetric. Okay? It's not even axially symmetric in a disk, but it looks more like a cloud that leaves the binary. So here I will show a movie that illustrates this interaction for the first passage of the star, but obviously there can be multiple passages until the companion truly enters inside the envelope and commences the true dynamical common envelope evolution. And you can see, hopefully, at least a little bit, that the material that is ejected is asymmetric. And although our work was initially motivated by the famous star VY Canis Majoris, it was very interesting to see this paper by the Beck from a couple of days ago, which was about NML Cygni, where they claim that they have seen multiple shells surrounding the star that are asymmetric and that are distributed in a way that would be broadly compatible with our simulations. So this paper is still something that I'm digesting and trying to understand, but it's exciting to see that our theory might actually be realized in nature. And a third possibility how a binary star can enter common envelope is through the Darwin instability. This happens when the amount of angular momentum in spin of a star is sufficiently large compared to the angular orbital momentum. So how can we understand that? Consider a star that's sort of macroscopic and large and a point mass companion, and tides over time will synchronize the spin and orbit. But what if the star expands? Conservation of angular momentum says that the spin will slow down, but the tides will try to spin up the star. In other words, to transfer angular momentum from orbit to the spin. But if you remove angular momentum from the orbit, the companion comes closer and orbits faster. And if there is too much inertia in the spin, then this process cannot be stabilized, and the companion spirals in on a tidal timescale. Eccentricity? No, this can happen even for a circular orbit. There is a separate eccentric instability in these equations.
Would the Darwin instability be the eccentric orbit?
Not necessarily. It will actually remain fairly circular. But Darwin instability is potentially quite important for a class of binaries that are called contact binaries, and I show their structure in the beginning. And what we believe is that these contact binaries are born with some mass ratio, but over time, secularly, they should evolve into smaller and smaller mass ratios until they encounter this Darwin instability, at which point they should merge and disappear. So if we imagine some kind of a mass ratio distribution, we should see it rising because the time scale for their existence increasing until there is a sharp cutoff, some kind of minimum mass ratio, which corresponds to this Darwin instability. And in my work with PhD student Milan Pešta, we looked at a method that was proposed by Slavek Ručinský in 2001, and we reformulated this method using Bayesian statistics and applied it to data from the Kepler satellite. And as a result, we could detect signatures of this Darwin instability, this minimum mass ratio, only in the distribution of photometric amplitudes. So we didn't need radial velocities. We didn't need to model the light curves in detail. And here on this picture, I'm showing the posterior distributions of this minimum mass ratio inferred from the data for different types of contact binaries, showing that there are differences between different populations that approximately trace our theoretical expectations. So after the binary enters common envelope, what it experiences is a dynamical plunging. And here I will illustrate this with a simulation that comes from a work of Ullmann et al. 2016. We actually, in my group, haven't done any simulations of this phase because this is something that was studied a lot by many people, and we sort of did not want to repeat what people have already done. So what the simulation will show is a red giant with a point mass core, and a companion will appear here. And what is going to happen is that the two cores very quickly come close together. That's the dynamical plunging. And the envelope is significantly perturbed and expands. Part of this envelope is ejected and leaves this binary altogether. And this is important because this dynamical ejection is associated with some kind of brightening that we can, in principle, observe. So on this diagram, I'm showing sort of the parameter space of astronomical transients, their duration in days, peak luminosity in solar units or physical units. The gray areas show transients that are relatively well known, like classical novae, dwarf novae, all sorts of supernovae. But what is really interesting are the objects in red, which are called luminous red novae, or they have other names. And people believe that these transients are sort of the counterparts of common envelope evolution. The best known example here is V838 Monocerotis, but really the sort of the Rosetta Stone for making the connection to binaries is V1309 Scorpii and the OGLE data that were obtained for this object. So I spent a lot of time in my life thinking about these transients, but sort of to boil things down to a single question, we still do not know what powers these luminous red novae. The original idea was that this dynamical ejection ejects potentially a large amount of hydrogen, and the recombination of this hydrogen can provide enough energy to power the transient that we observe, similarly to type 2 plateau supernovae, but sort of scaled down in many aspects. The problem with this model is that some of the bright events that are outside of our galaxy require huge amounts of hydrogen, sometimes even hundreds of solar masses of hydrogen to explain the light work. So we sort of need potentially some other way how to extract more energy from a gram of material that is ejected. And that mechanism is potentially a shock interaction. So if you remember what I was saying about mass transfer, that it's non-conservative and it leaves the binary to surroundings in some form of a disk, then what happens later when the companion plunges in and ejects something dynamically and faster, these two components of the ejecta collide together. There is a radiative shock which thermalizes this kinetic energy, and this can actually lead to powering of the transient and making it quite a bit bright. So over the past few years, we have been working on the two-dimensional radiation hydro simulations of these transients, where we used moving meshes and realistic microphysics like equation of state and opacities, because for these transients, it's sort of a complication that is necessary. And what is shown on this movie on the left is a density distribution. You can see the two components, the disk and dynamical ejection. And on the right, you can see radiative energy density, and the arrows show radiative flux. And what is important is that there is this shock, and the flux that is coming out goes also laterally. That means that the radiative flux is distributed throughout this envelope, and what we see from outside is potentially almost spherical transient that appears like it was powered by hydrogen recombination. So these results still remain to be finished, and I'm hopeful that will be done soon. But let's move forward in the evolution of common envelope into this phase of self-regulated inspiral. You might have noticed in the simulation of Ullmann et al. That in the end, the two cores were orbiting around each other really, really fast. So this is visualized here, where we have distance as a function of time. And you can see that maybe the distance is decreasing, but way slower than before. And here in this case, we had a realization that at these late phases, the binary effectively looks like a circumbinary disk that is very thick. Okay, so a binary star surrounded by a disk. And when you say that, I mean, it sounds sort of trivial, but when you say that, you can immediately connect common envelope evolution into a much bigger literature on circumbinary disks, where we understand already a lot of things. So exploring this connection was task of my postdoc Damien Gagnier, who performed long three-dimensional simulations with Athena++. And initially, what he did was that he used spherical coordinates and excised the central region. So there was some inner boundary condition, and he placed the binary inside this inner boundary. So what it means is that there were 2-point masses going around, gravitationally perturbing the surrounding envelope. And what that allowed us to do was to use high resolution and run the simulation for a long time, because we were not restricted by the time step close to the center. So what we find out, for example, in this simulation with magnetic fields, is that the envelope on its own is apparently not able to develop large-scale bipolar outflows, something like jets. The magnetic energy is amplified and increases, but it never organizes into something like a polar outflow. We also investigated in in more detail the transport of angular momentum and found out that the binary still continues to shrink on a time scale of thousands or maybe up to million orbits. And that is quite important because we cannot simulate in 3D, perhaps not even in 2D, the system for such a long time scale. So that connects back to the original problem that we do not have the right tools to describe everything that happens in common envelope. And in the last paper of Damien, which actually was finally published in ANA also today, we decided to, or rather he decided to take a different approach and instead constructed a multiple nested zoom-in simulation of the central region. And what was very interesting to find was that the 2-point masses in the center are able to sort of accumulate mass around them in a quasi-hydrostatic structure. And as a result, it looks like inside common envelope, we have something that looks like a contact binary. Okay, the two stars sharing a common hydrostatic gaseous envelope. And another interesting thing was finding that we actually get jets that are quite weak, but we do not require magnetic fields. What happens is that the envelope has a lot of angular momentum, and as a result, it opens up nearly empty funnels along the poles, and shocking of the gas close to the binary leads to heating, and the material can escape through these open cavities. So that were the results of the work that we have been doing over the past few years. But while we were doing that, I've been constantly wondering that we do not really have good tools for simulating binary stars in the computer. The reason for this is that binary systems don't really have any useful symmetry that is commonly exploited in astrophysics, right? Something like a Roche potential is not spherically symmetric, is not cylindrically symmetric, and even many of the mirror symmetries are removed by the Coriolis force. So the way people usually treat this, there are several ways, but one of the most common ones is that people simply put some kind of a Cartesian mesh on top of the binary. But it leads to problems because when mesh is not aligned with the expected solution, there are numerical artifacts. And the traditional methods also require quite a bit of communication between individual cells, called stencil, in this numerical work. So, you know, the whole thing was to me quite puzzling because the traditional approaches do not work well, but at the same time, we in many cases know almost exactly how the solution looks like, right? We understand Roche potential, we know how circumbinary disks look like, so we should be able to do something about it. And that's the goal for the new project, which starts in about 6 weeks. And the goal is to develop a new code in 3D that is specifically adapted to studying binary stars. And in addition to using these adapted meshes, we are also moving to use something that's called discontinuous Galerkin method, which is something that mathematicians have studied for a long time, but in astrophysics, it has so far had only limited applications. So the goal is to develop this code and apply it to many types of binary systems and hopefully solve many of the open problems, you know, including structure of contact binaries, which is something that personally troubles me a lot. And I couldn't finish without mentioning that we will have open positions for PhD students and postdocs opening in the fall. So that's all from me. Thanks for your attention.
you. Thank you very much, Ondřej. An impressive work. Do we have any questions or comments?
So I start with the simple one. In the one of the very first slide, you put that the importance of the massive stars, you put that producing the compact object, and you put the white dwarfs. So this is not mistake.
Okay, I think I have. Well, the massive stars are in.
Okay, and
are
not the compact object. There are white dwarfs.
Yes. They are compact.
Yeah, but they are not the effect of the massive star.
They are result of stars.
Of stars.
So-
Okay. Okay.
So there is a parenthesis in there.
The second one, the most of this simulation did not show how these bipolar impressive structures are formed, and it just shows in the last slide that there is like the empty space, which is.
Okay, yeah, you're asking about. Okay, well, so I unfortunately don't have solution for ADA Carina or 1987A yet. Okay, there are ideas, but they require work. But the last picture that I was showing, okay, I should not have done that. Okay, sorry. Let me fix that for the people on Zoom. Okay, that was a mistake. Okay, so the last picture that I was showing here, right? This would be sort of relevant, or rather the thing that people have in mind in this situation is something like planetary nebulae, where we have sort of some ejection and maybe there is a jet that is coming out. And it was very interesting to see that we get polar outflows without even having magnetic fields in the simulation. So these outflows are generated and collimated purely hydrodynamical. They are quite weak, and it is true. It was published a couple of weeks ago by Marco Vetter from Heidelberg that if similar simulation includes magnetic fields, this jet becomes faster and more stable. So the magnetic field definitely helps to drive it, but even without that, we get sort of weak intermittent outflows.
Okay, so I'm looking into the common growth more from the binary population synthesis angle. And the question I have is how wrong or how right is this formula to show that this alpha CE prescription?
Okay, yeah, that's a good question. I can say, Damian, he to quote my former postdoc, when he read about this alpha formalism, he was like, I don't understand it. Okay, and it's like, okay, what's there to not understand, right? And this depends how you look at it, right? If you're sort of coming from population synthesis and from the global picture, right, it makes sense to have some kind of alpha in there. But if you sort of embrace the full complexity, like it's unlikely that you would be able to capture everything in the single parameter. And okay, so that is what maybe my answer is that I think from what we have learned about common envelope in recent years is more of a motivation for maybe these two-stage formalisms, because what we know is that there is some mass loss during the dynamical plunging, but potentially also a lot of mass is lost later when the two cores orbit inside the envelope, and this can be maybe subdominant is these magnetic outflows. There are apparently recombination driven outflows that are coming out, effectively disk wings from the circumbinary disk. And right then that's sort of not well described by alpha that just captures total amount of energy. So I think in the future we will be able to write better simple formulae that could be used. But I think there is still work to even understand what we see in the 3D simulations. Okay, did I evade successfully your question? I don't know, you know.
Yeah, I think that there were some attempts to parameterize alpha, so to have different alphas for different types of stars, and there was the Chinese formula, the other and others. So at this stage, can you provide some improvement of that formalism, or it's too early for that, or maybe that's not the goal?
You know, I definitely don't have that, and I would say, you know, I admit that it's maybe immediately very high on my list. Okay, I would rather understand what is happening there than provide sort of a single number. But you know, you said that there are, you know, one could vary the value of alpha depending on the stars. You know, sure, that's possible, right? Just you know, imagine that there are a number of parameters or real parameters that affect things, right? We should be always able to project this multidimensional space, you know, to find like the direction of maximum variation and sort of, you know, parameterize it this way. But, you know, does it mean anything physically? I mean, I don't know. You know, I am more interested in understanding what happens.
I think that you know, this is like two different things that always, when you try to understand something, you neglect some other things. So depending on what is the particular problem you want to solve, you will do this or that. So for the purpose of general binary evolution, you know, we don't really care what's happening exactly in minus 1000 orbits and plus 34 orbits. Just, you know, what's before and after. But you know, what is happening there is of course extremely interesting. So
Okay, and you know, maybe I can conclude by saying that I think, you know, sort of us, you know, the simulation people should have a duty to provide some kind of alpha. Okay, because I don't know. I think that in the end, that's sort of the only way how to connect these two worlds. I mean, there's, you know, you cannot include 3D simulation for every trajectory. So there needs to be something like alpha, and that should be figured out by the theorists.
So I have a question with regard to the codes. So do you plan to implement any like adaptive pressure refinement or any like complex techniques to handle separation of scale in those?
Yeah.
Or is it not important here?
Yeah, so we used Athena++, so it already has static and adaptive mesh refinement, and for these simulations we use both static and adaptive mesh refinement. And for this simulation, we used only static mesh refinement in Cartesian coordinates, but a large number of levels. There are 7 or 8 levels of refinement that really focus on the central regions.
And what about the new code, which is the code?
Yeah, for the new code, that is an interesting question. So that remains undecided. And what is an interesting development is GPUs, right? On a single GPU, we could run a box that's maybe 256, maybe 384 cubed, which is already quite substantial. So maybe what is possible, instead of, you know, adaptively refining some regions, we could just use a lot of GPUs to have high resolution everywhere. Because, you know, really the GPU is factor of 100 improvement. So.
Marek.
So having the measure every 5 years is everything asked about gravitational waves. Can the spectrum be visible in LISA, or maybe some parts of the spectrum can go even to ground-based detectors?
Yeah, so there are a couple papers that looked at gravitational wave signatures of common envelope evolution, and since these stars are they are not compact objects typically, at least one of them. The frequencies are quite low, so it's more in the Lisa band. But if I remember correctly, the conclusion was that Lisa is not sensitive enough, and maybe it will be detectable by the next generation, like Desigo. Anyway, that's kind of all I know about this. Okay, so some people have thought about it, but it's not, immediate. It's not immediate.
There's one more question on Zoom. Łukasz. Can you hear us, Łukasz? Seems frozen.
Okay, well, he moves.
Ah.
I think I lost sound from your side, but I guess you can hear me.
Yes.
Okay, there's some issues with the sound. Hi, Ondřej. Hi, good to see you, at least remotely. So I wanted to ask about the, how many new cases you need from the observational side. Of course, LSST will probably flood you with new examples, but they will be kind of useless. Do you agree? Because they will be faint, and you need them well observed and well studied. So could you give as a hint, ask the observers, give a hint what kind of data you still need from the observers in terms of transients, of course. Yeah.
Okay, so I think still in terms of extragalactic events, we do not know that many, like maybe 20 or so in total. So detailed studies of these individual objects can still bring many new things. But I would, to some extent, disagree that LSST will be useless, because with LSST, it might be quite possible to record what happened before the outburst. So, imagine what Ogle obtained for V1309 Scorpii. Now LSST might be able to do for extragalactic events, which would be a huge thing. I would say that Nadia Blagorodnova is the right person to ask about these issues. So she would be able to answer much more thoroughly. Maybe one last point, which is also something I've been thinking about recently, is that now with JWST, we should be able to probe in infrared what happens after the optical maximum. So we know for these transients that a lot of them, basically all of them, get enshrouded in dust. The optical emission becomes quite weak, and JWST or other infrared tools could be very useful to better understand what's happening there.
Okay, thanks.
Thank you. I don't see any more questions and comments. So thank you, Ondřej, and congratulations on your work. And hopefully you will come to our observatory a bit earlier than in 8.5 years or whatever it has. So we're solving all the mysteries you mentioned. Okay, next week there's kind of well, let's call it interesting seminar about the intersection of video games and astronomy. So they're going to be an expert saying about using catalogs of stars and some also information from astronomy in video games. So feel invited, and the notebook is somewhere here. So see you next week. Thank you very much.